Hello guys, and welcome back to my channel or the Big Structural Hub. This is the #1 channel for structural insight and a place where you learn, build and innovate. This channel brings you at least 2 videos every week, but I'm sorry I never updated any video last week due to the reason that I will not explain. And today we resume from where we left, and the session for today is all about continuous one-way spanning slab to Eurocode 2. As you can see on the board, we want to tackle continuous one-way spanning slab. In this session, we will know what is a continuous one-way spanning slab and what are the method of analysis. Then from there, we'll tackle a question or an example, and the example will summarize what we call continuous one-way spanning slab. So stay tuned as I start up to the end. But for those who have not subscribed to the channel, I do encourage you to subscribe and be a member. Turn on the notification bell so that you may be the first person to be updated when I upload a video. So we go back to our topic of today. Continuous one-way spanning slab to Eurocode 2. So when you hear this word continuous, what comes into your mind? So for a continuous one-way spanning slab, these are slabs spanning at least 3 supports. So for example, if you have a slab like this one, which is resting on more than 3 supports, then automatically this is what we call continuous slab. So this is the same as to continuous beam. So it is designed the same way as to continuous beams. So what are the method of analysis? So before you design such a continuous one-way spanning slab, it is a must you know the method of analysis that you will use. So these are the methods. Number 1, we have the simplified method, and then number 2, we have the formal traditional analysis. So we will begin by simplified method. So this simplified method, we use a coefficients. This is the same as to a continuous beam design. So for you to use these coefficients, there are requirements that your slab, your continuous one-way spanning slab has to meet so that you can use this simplified method. And what are these requirements? So number 1, we have the loading must be UDL. So the requirements, let me put them on the board. So we have the requirements. For you to use a simplified method. Number 1, the loading must be UDL. So the loading must be uniformly distributed load for you to use such a method. Number 2, we have the QK must not exceed GK. QK must not exceed GK. So in other words, GK must be greater than QK. Condition number 3, it says that the slab must be continuous over 3 or more spans. So the slab must be continuous over 3 or more spans. So if a slab has 3 or more spans, then you can use this method. So this is what it means. So for a slab to have 3 or more spans, it means that you must add one. You must add the number of slab. You add 1 so that you can get the number of supports. So here the support will be 4 and above. So how many spans are here? These are 1, 2, 3, and 4. And then the support are 1. Let's use A. This is A, B, C, D. So it means 3 spans and above, and then 4 supports and above. We move to condition number 4. Condition number 4. Condition number 4. The span in variation must not exceed 15% of the longest. The spans in variation must not exceed 15% of the longest. 15% of the longest. So this one, it means if you have a span with different effective lengths, let's say 2, 4, or we go with 2. Let's go with 2, 3, 4, 6. So if you come here, the spans has effective length of 2 meters, 3 meters, 4 meters, and 6 meters. So the smallest is 2 meters and the longest is 6 meters. So you will get the difference between 2 and 6. So that is, no, you get the variation between 2 and 6. So this is 2 minus, no, 6 minus 2 is 4. So 4 over 6 times 100%. So what is the variation in length? What is the variation in length? So let's see. If the variation exceeds 15%, then we should not use this method. So this is 4 over 6 times 100. So this is 66%. This is 66%. Therefore, you're not supposed to use this method in such a case. So after your slab has met this condition, this is the table that will help you in calculating the design moment and the design shear force. So here is the table. So this is the interpretation of the table. So you have the end support, and then you have the end span, penultimate support, interior span, and interior support. So each of them have their formula for calculating MED and VED. For example, so that is a slab. So the end support, these are the end support. These are the end support. End support. And then you come to end span. So this here, 1, 1. So these are the end span. End span. And then you come to penultimate support. penultimate support is the support which comes after the end support. So this one here, this one and this one are the penultimate support. Penultimate support. And then we have the interior span. So here, this one is the interior span. And then the interior support. The interior support is the one which comes after the penultimate support. For such a slab, there is no interior supports. So these are the formulas I have said. MED is the design moment and VED is the design shear force. For example, for end support, the design moment is 0 and the VED is 0.4 F, whereby F is equal to 1.35 GK plus 1.5 QK times 1 meter width of the slab. Times 1 meter width of the slab. And then the L is equal to effective span. For example, if you want to calculate MED for end span, you will use this formula 0.086 FL. So L is the effective span. Example, we want now to tackle an example regarding this. Before you go to example, we have the second method. We have the second method, which is the traditional analysis method, formal traditional analysis method. So for this method, if the slab is not meeting any of these conditions I have highlighted here, then you are supposed to use the formal traditional analysis method. And an example of this is, number one, we have the moment distribution method. Number two, we have the slope deflection method. So we have the third one, which is a three-moment theorem, or the Clapeyron theorem. So these are the methods you will employ if your slab will not meet the condition or the requirements already talked about earlier. So after having done so, I want now to do an example, or to tackle an example regarding what we have discussed before. So these are the example. So I will read the question, and the question goes like this. You are the lead engineer for a residential development. You are tasked with designing a slab spanning across 4 parallel beams as shown below. On the floor plan, using Eurocode 2, determine the most suitable effective depth of the slab, overall depth, and hence bending reinforcements. So these are the data. QK is equal to 4 kilonewton per meter square. These are the QK. Finishes is equal to 1 kilonewton per meter square. So these are the finishes. And then you have the partitions is equal to 1.2 kilonewton per meter square. Here it is. We have the nominal cover is equal to 25 millimeter. Here it is. And then we have the FCK. This is the strength of concrete, which is 30 Newton per millimeter square. And then we have the strength of steel, FYK, which is equal to 500 Newton per millimeter square. And then, of course, we have the unit weight of concrete. Here it is, 24 kilonewton per meter cubic. So this is the slab. This is the floor plan. As you can see, this slabs is resting across 4 beams. So 1, 2, 3, 4. So these are the slab, and it is a continuous slab. So if you cut across this slab like this and observe in this direction, So this is section XX. So this is what you will see. If you cut across section XX, this is what you will see. So this plan has dimensions which are 400, no, 4,000, 4,000, 4,000. So it is spanning 4,000, 4,000, 4,000. And then the longer distance is 9,000 millimeters. So these are the longer distance, which is 9 meters. And then we have the span, which is 4 meters or 4,000 millimeters. So let's see how you can design such a slab. Solution. So before you can proceed to designing this slab as a one-way continuous slab, it is a must we check first. It is a must you check first whether it is a one-way or not. And to confirm, this is how you confirm the ratio of Ly all over Lx must be greater than 2. This is for a one-way spanning slab. So the Ly is the longer distance, which is 9 meters. So this is 9 all over the shorter distance, which is Lx, that is 4. So this one is equal to 2.25, which is greater than 2, and therefore a continuous one-way spanning slab. So we are going to design it as a one-way continuous spanning slab. So therefore, the first thing to determine or calculate is depth determination. So we have the depth determination. And for depth determination, you will first assume the reinforcement ratio. So assume reinforcement ratio. So this is from the code. So we'll assume 0.35%. So remember, this is a lightly reinforced concrete. So for a lightly reinforced concrete, the maximum is 5%. So assume a lightly reinforced concrete 5% and below. So the reinforcement ratio will be 35 all over 100. So change this 0.35 from percentage into fractions. So this one is equal to 3.5 times 10 raised to power negative 3. So to determine depth, you need this formula. L over D is equal to and this is expression 8.32 of Eurocode 2. So this is expression 8.32. So this expression will help you to determine the basic depth ratio for effective length over depth all over effective depth. So K is obtained in table 8.11. So table 8.11, which is 1.3. I will show you later. And then we have so this table 8.11, which will give us 1.3. So for a continuous beam, this will be for what we call end span. So this is for the end span. And also K is equal to 1.5. So this is for the interior slab or interior span. But we'll use the end span in our calculation. So we proceed. You have seen that the reinforcement ratio is equal to 3.5 times 10 to the power of negative 3. And then we have another term in this formula which will define. So this one is equal to FCK square root of FCK times 10 to the power of negative 3. Here it is. No, here it is. So this one is equal to FCK is 30 raised to power a half or square root of 30 times 10 to the power of negative 3. So this one is equal to 5.48 times 10 to the power of negative 3. And then another term to define is from the formula 1.5 this one FCK. So this one is equal to 1.5 times square root of 30, which is equal to 1.5 square root of 30. So this is 8.21. And then we proceed to another term, which is 3.2 FCK, square root of FCK. Here it is 3.2. So this one is equal to 3.2 root 30, or 3.2 30 raised to power a half, or 0.5. 3.2 times 30 raised to power 0.5. So this is 17.53. Then you can insert these values, the known values, into the formula. So L over D is equal to K, as we have said, we'll use for the end span 1.3, like that. Then 11 plus this one is here 8.21 into bracket. This one is here 5.48 times 10 to the power of negative 3 all over 3.5 times 10 to the power of negative 3, like that. Then plus, we come to this one. We have 3.2 root FCK. Here it is. 17.53 into bracket 5.48 times 10 to the power of negative 3 all over 3.5 times 10 to the power of negative 3, then minus 1, and then 3 over 2, like that. So, and then you put the larger bracket like that, like that. So L over D, if you punch your calculator, you will get 41. So this is the basic ratio. Basic ratio. Let me show you how to obtain this K first, and then we proceed. So this is table 8.11. This is a table for basic span over depth ratio for reinforced concrete members. So as you can see, the first one is for the simply supported beam and the slabs. And then for the second one is the end of continuous beams and slab. So for this one, K is 1.3. As you can see for our case, this is the end span of beam, that is 1.3. And for a lightly reinforced concrete, as you can see, the reinforcement ratio is 0.5%. So when you pick this one, it should be below 0.5%. And then you come to the interior spans of continuous beam and slab. This is 1.5. So 1.5, that is for K. And then, yes, that is it. So we will use the end of continuous slab or the end span, which has a K of 1.3. Let me erase here. So we know that L over D is equal to 41, but L is equal to effective length, which is equal to 4 meters in our case. So L, which is 4, over D is equal to 41. So you can easily get D by making D the subject of the formula, which imply D is equal to 4 meters all over 41, which is equal to 98 millimeters. 98 millimeters. So 98 millimeters is our D. So D is equal to 98 millimeters. So as a designer, you must choose a D which is reasonable. So this one is slightly lower. So you'll say adapt D as 120 millimeters. So our new D is 120 millimeters, which is greater than 98 millimeters. Therefore, to calculate H, now H determination. So H is the overall depth of this slab. So to calculate H, you will assume diameter of main steel as 10 millimeters. So assume diameter of main steel as 10 millimeters. Therefore, H is equal to D plus main diameter over 2 plus nominal cover, like that. So this one is equal to, our new D is 120 plus 10 all over 2 plus our nominal cover here is 25 millimeters. Therefore, H is equal to 150 millimeters. So our overall depth of the slab is 150 millimeters. And then from there, you can now calculate our loading, or we can do the load analysis. So load analysis, remember this is the overall depth of the slab. Overall depth of the slab. So the next step is load analysis. So allow me to clean here. So load analysis. So for load analysis, we will start by the on weight of the slab. So on weight of the slab. And to calculate on weight of the slab, we will use our overall H, or H, which is 150 millimeters, and unit weight of concrete, which is 24 kilonewton per meter cubic. Therefore, to get the on weight of the slab, take 150, change it to meters, so divide it by 1,000. So this one will be meter, then times the unit weight of concrete, which is 24 kilonewton per meter cubic. So here 1, here meter square. So the final answer will be 3.6 kilonewton per meter square. So that is the on weight of the slab. And then the total GK, this is the permanent action, is equal to 3.6 plus the partitioning. You have the partitioning, which is 1.2, then plus the finishes, which is 1. So all of these are in kilonewton per meter square. So here you will get 5.8. You will get 5.8 kilonewton per meter square. And then we have the QK. So QK, so this is the variable action. Here it is 4 kilonewton per meter square. And then from there, we'll see if we'll employ what we call the formal traditional analysis method, or the use of coefficient method. So for the use of coefficient method, we have seen that the requirement are GK must be greater than QK, which is okay. You can see 5.8 is greater than 4 kilonewton per meter square. And then the second one, it must be a uniformly distributed loads, which is okay. So the QK is a UDL and the GK is a UDL. And then the number 3, the variation in spans must not exceed 15%. As you can see, the variation in span is less than or is 0%. So this one is okay. Variation in span, variation in spans. So this is percentages, is okay. And then the fourth one, the the spans must be 3 and above. So spans 3 and above. We can count. We have the first span 2, then 3. Therefore, okay. After doing so, you can see this slab, it is meeting all the requirements to use the coefficient method, and therefore that is what we are going to use. So we proceed to design ultimate load design which is given by 1.35 GK. Let me write it here. 1.35 GK plus 1.5 QK, and then times 1 meter width of the slab, like that. Therefore, this one is equal to 1.35 times GK. You have seen it is 5.8 plus 1.5 times 4, which is QK. And then multiply everything by 1 meter. So this one is equal to, you'll get 14.23 kilonewton per meter. So this is the design ultimate load. And from there, we can again calculate loading on full length. So loading on full length. So this one is equal to, you take the design ultimate load, which is 14.23 kilonewton per meter, then times the span, which is 4 meters. So meters will cancel with meters. So this one is equal to 56.92 kilonewton. And this 56.92 is what we call F, like that. So F, we have 56.92, and then L is equal to 4 meters. And then from there, we proceed to design moment and shear forces. So we will start by, no, let's proceed to design process. Allow me to clean here. So F is 56.92 kilonewton, and then L is 4 meters. You can write them somewhere. So design process. So we begin by what we call support AA or DD. You can see this is the end support. So we begin by end support, and supports, which is AA and DD. So end support. For this, we'll use the table which I have already provided. So I'm not going to draw the table again. So you can just check on the table, whereby MAD for the end support is 0 kilonewton meter. And then the shear force, VAD, is equal to 0.4 kilonewton. But since we have 0 kilonewton meter for end support AA and DD, we are not going to design for bending reinforcement for this because it has 0 kilonewton meter. And again, we are not going to design for the shear because the clause, no, for the code state that a slab which has an overall depth below 200 millimeters, there is no need to provide shear reinforcement. And for our case, our H is 150 millimeter, and therefore no need to proceed to such. So we are already done with end span, or no, end support AA and DD. Then we proceed to what we call span AB and ED. So this is end span. We proceed to end span and spans. So this is span. You can see span AABB. This span, this from here to here. So spans, end spans AA, BB, and BD, CC, like that. So for if you proceed to the table, you will see that the end span MAD is equal to 0.086 FL, 0.86 FL. So this one is equal to 0.086 times F. We have already calculated F, which is 56.92. Then times L. L is the effective length, which is 4 meters. So times 4. So this one is equal to 19.58 kilonewton meter. And VED from the table is 0 kilonewton. Therefore, area of steel is equal to MAD all over 0.87 FYKZ. So before we come to this formula, let's first calculate this. K naught is equal to MAD all over FCK BD square. So this one is equal to MAD is 19.58 times 10 to the power of 6. Change it from kilonewton meter to Newton millimeter all over FCK. FCK is 30 times B. B is 1 meter width of the slab, which is 1,000, times D, which is 120 square. So you will get 0.045, and therefore 0.045 is less than 0.167. So no compression, therefore no compression reinforcement. Is needed. So no need to provide compression reinforcement. And then we proceed to Z. So in our formula, we will calculate Z. So Z is equal to and remember, it must be less or equal to 0.95 D. So if it exceeds this one, then this 0.95 D, we will use it as our Z. So we proceed. So Z is equal to D is 120, then 0.5 plus 0.25 minus 3 times K naught is 0.045, 0.045, like that, and then all over 3.4, and this one is raised to power 0.5 or a half, like that, and then you put the larger bracket. So Z is equal to, if you punch your calculator, you will get 0.96 times 120. So this one is greater than 0.95D, and therefore our Z will be 0.95D, which is equal to 0.95 times 120, which is equal to 114 millimeters. So this is our Z, and therefore we can now determine the reinforcement areas, whereby area of steel is equal to M over 0.87 FYZ. So this one is equal to M is 19.58 times 10 to the power of 6 all over 0.87 times FYK Z. So FYK is 500 times 114. So this one is equal to 395 millimeter square. And then from the table, I hope you know how to convert this area into the size of bars and their spacing. So if you don't know, you can let me know through comment section. So from table provide H10. Remember to maintain the one we assumed, H10 at 175 millimeter center to center, and area of steel is equal to 449 millimeter square. At the bottom of the span, AB, of span AA, BB, and DDCC, because it has positive moments. So this span from here to here and from here to here, it has positive moments, the same as from here to here on the plan, and from C to D. Those they have positive moments. And provide H10 and provide H10 at 175 millimeter center to center, area of steel is 449 millimeter square. At the top in the top of supports, these are the penultimate supports. In the top of supports B, BB, this support BB and CC. Why are we providing the same size of bar and the same spacing? Is because MED for penultimate support is equal to negative 0.086 FL. So the formula remains the same, but what changes is the sign. So the first one for span AA, BB, and CC, DD was positive 0.086 FL. So for this support, the penultimate support, the formula remains the same, but the sign changes. So to avoid a lot of calculation, just write a statement and say that provide H10 at 175 millimeter center to center, area of steel 449 millimeter square in the top of supports BB and CC, because where we have a negative moment or a design moment, we always provide reinforcement at the top, and where we have positive, we provide at the bottom. So provide H10 at 175 millimeter center to center at support BB and CC, and by doing so you have avoided a lot of calculations. After doing so, we will proceed to what we call check estimated effective depth of end slab or end span. So we'll check whether the estimated effective depth is okay or not. So we'll say check estimated effective depth of the end span. Slab. So for this one, so we'll start by calculating the design service stress. So design service stress, which is given by 5/8 FYK times area of steel required over area of steel provided. So design service stress is equal to 5/8 times FYK is 500, then times area of steel required. This one is 395, and area of steel provided is 449. So this one is equal to 275. And then the modification factor is equal to 310 over design service stress. So this one is equal to 310 all over 275. So this one is equal to 1.1. So our K is equal to 1.1. And then you can now write the formula. L over D is equal to so this is the formula for basic ratio. We will define the terms in this formula and we will begin by the reinforcement ratio. For this time, we will not estimate the reinforcement ratio because we already have the area of steel required. So this one is given by this formula. Area of steel all over BD. So area of steel will be 395. This is the area of steel required over B. B is 1,000 times D 120. So this one is equal to 3.29 times 10 to the power of negative 3 or 0.33%, like that. So we proceed. So L over D is equal to K, which is 1.1, 11 plus 1.5, FCK is 30, like that. Then this one, it remains the same, 5.48 times 10 to the power of negative 3 all over, sorry, this one will change, 3.29 times 10 to the power of negative 3, you close the bracket, plus, we come here, 3.2, FCK is 30, into bracket, 5.48 times 10 to the power of negative 3 all over 3.29 times 10 to the power of negative 3 minus 1 raised to power 3 over 2, like that. So if you punch your calculator, you'll get L over D is equal to 38 is equal to 38. So this is what we call modification allowance. Modification allowance. Modification allowance ratio, like that. So the actual span or effective depth, the actual span, actual span all over effective depth ratio is equal to 4,000 all over D. D is 120, so this one will give us 33, like that. Therefore, 33 is less than 38. So the slab is okay. We'll say therefore the slab is okay. The slab is okay and meets deflection requirements. Deflection requirements. Therefore, use a slab of effective depth, which is D. D is equal to 120, H is equal to 150 millimeters, and main steel H10 at 175 millimeter center to center. So we have already finished what we call the design of span, the end span, which is span AA, BB, span DD, CC, and also the penultimate supports, which is support BB and CC. Then from there, we'll proceed to check the spacing and areas, and then the secondary bars. So we now proceed to the spacing and areas. We check for spacing and areas. So we know that for maximum for main steel, maximum for main steel, remember this is for spacing, we will use this one. 3H must be less or equal to 400 millimeters. So this is generally. So 3H is equal to 3 times 150, which is equal to 450 millimeter, and therefore 450 exceed 400. So we'll use our maximum as 400 millimeter. Therefore, 175 millimeter center to center is less than 400 millimeter. So, okay. We proceed to in areas of maximum moment, in areas of maximum moments. So in areas of maximum moments, we'll use this formula. 2H must be less or equal to 250 millimeters. So 2H is 2 times 150, which is 300 millimeters. So 300 is greater than 250. Therefore, our maximum will be 250. And therefore, 175 millimeters center to center is less than 250 millimeters. And therefore, okay. We proceed to areas. So areas, let me clear. So we know that the maximum areas, or AS maximum, is equal to 0.04 AC, whereby AC is the area of the concrete. So this is 0.04 times AC is BD. No, it's BH. BH. Let me write it here in the bracket. BH. So B is 1,000. This is 1 meter width of the slab times H, which is 150. So this one is equal to 6,000 millimeter square. And then the area of steel minimum is equal to 0.26 FCTM over FYK BTD. So this one is equal to this one, whereby FCTM is given by this formula 0.3 FCK raised to power 2 over 3. Therefore, area of steel minimum is equal to 0.26 times 0.3 times 30 raised to power 2 over 3 all over FYK is 500 times BT. This is 1,000. Yes, this is 1,000 times 120. So this one is equal to 181 millimeter square. 181 millimeter square. And remember, AS minimum must be greater or equal to 0.0013 BTD. So this one is equal to 0.013 times 1,000 times 120. So this is 156 millimeter square. So the expression is 0.04 AC must be greater or equal to AS1. So this is the area of steel required, not the area of steel provided, and this one must be greater than 0.26 FCTM over FYK BTD, and must be less or equal to 0.0013 BTD. So as you can see, everything is okay, whereby 6,000 is greater than 449, which is greater than 181, which is greater than 156. So this one is SC, no, 0.04 SC. This one is the area of steel provided. 181 is this one, and then 156 is this one. So therefore, okay. Therefore, okay. Then we proceed to secondary bus. So we have the secondary bus, or a distribution bus. So for the secondary bus or distribution bus is given by this formula. So AS minimum is, this one is given by area of steel minimum, which you have already calculated, and our under is 181 millimeter square. So remember, area of steel minimum is given by this formula, 0.26 FCTM, and then times times BD. So this is the formula for area of steel minimum, but we have already calculated it and got 181 millimeter square. So from this 181 millimeter square, you'll say provide from table 3.22, provide H8 at 250 millimeter center to center, and area of steel provided is 201 millimeter square. And then we check for maximum bar spacing. So maximum bar spacing. So we have S max is equal to 3.5 H, must be less or equal to 450 millimeters. So 3H, 3.5 H is equal to 3.5 times 150. So this one is 525 millimeter, which is greater than 450 millimeter. So our maximum spacing will be 450 millimeters. And then from here, 250 millimeter center to center is less than 450 millimeter. Therefore, okay. So this is for general. And then for max area of maximum moment, this is where the maximum moment is high. So this one is given by this formula. 3H must be less or equal to 400 millimeters, like that. So 3H is equal to 3 times 150, which is equal to 450 millimeters. So 450 is greater than 400, therefore 400 will be our maximum. Therefore, from 250 millimeter center to center, so 250 millimeter center to center is less than 450 millimeter. Therefore, okay. We now proceed to span BC. Span BB, span BBCC. So this is the interior span. interior span, this one from here up to this point. So for interior span, MED, from the table, this is the coefficient table, is given by 0.063 FL. So this one is equal to 0.063, F is 56.92 times L, L is 4. So this one is equal to 14.34 kilonewton meter. Then VED is equal to 0 kilonewton. So area of steel is equal to MAD is 14.34 times 10 to the power of 6. Why? Because we are changing from kilonewton meter to newton millimeter. All over 0.87. Fy is 500. Then Z is remain the same, 114. So this one is equal to 289 millimeter square. Then from the table 3.22 provide H10 at 250 millimeter center to center, and then area of steel is equal to 314 millimeter square. Then this one is provided at the bottom. At the bottom of slab, because it has a positive moment or a positive design moment. Then from there, we will check estimated effective depth, or D, of interior span. We'll start by calculating the design or the service stress, which is given by 5/8 FYK times area of steel required over area of steel provided. So this one is equal to 5/8 times 500 times area of steel required. This is 289 all over 314. So this one is equal to 288 Newton per millimeter square. And the modification factor is equal to 310 over service stress, which is equal to 310 over 288. So this one is the same as for our first case, which is 1.1. And therefore, from this formula, L over D is equal to K plus 3.2 FCK minus 1 raised power 3/2. Then you close the bracket, whereby the reinforcement ratio for this case, or at this point, will not assume. We will now calculate using this formula AS1 over BD. So this one is equal to 289 over 1000 times 120, which is equal to 2.4. 1 times 10 is power negative 3, or 0.24%. 0.24%. So from there, we can now insert the known into the formula, whereby L over D is equal to, our K here is 1.1 into bracket 11 plus 1.5 root 30 all over, this one made the same, 5.48 times 10 to the power of negative 3 all over 2.41 times 10 to the power of negative 3, like that. Then plus, we come to this one, 3.2 root 30 into bracket 5.48 times 10 to the power of negative 3 over 2.41 times 10 to the power of negative 3 minus 1, close the bracket, raised to power 3 over 2, then the larger bracket. So this one is equal to, let's carry out the operation, is equal to 37, and then we'll say actual span over depth ratio is equal to 4000 over 120, which is equal to 33, and therefore 33 is less than 60.37. So you will say, therefore, the slab is okay, and meet deflection requirements. Therefore, use a slab of D is equal to 120 millimeters, H is equal to 150 millimeters, and main steel is equal to, or main steel as H8 at 250 millimeter center to center. So for this plan, there is no interior support. Therefore, this is the design that will. This is the end of the design, but we have to check for spacing and areas. So we check for spacing and areas. Allow me to clean here. So we have the spacing and areas. So for spacing and areas, you see that at 250, the center to center distance is equal to 250 millimeter. And from previous calculation, we saw that the X maximum is equal to 400 millimeter center to center. So 250 millimeter center to center is less than 400 millimeter center to center, therefore okay. Therefore okay. And then in the areas, so this is for general, and in the areas of maximum moment, so areas of maximum moment, again from the previous spacing check, we saw that the M max or the S max, not the M max, the S max was 450 millimeter, and therefore 250 millimeter center to center is less than 450 millimeter, therefore okay. We proceed to maximum area. So this one, we know that from our previous calculation, 0.04 AC, we got 6,000 millimeter square, and then the value will remain the same, and then 0.26 FCTM all over FYK BTD was 181 millimeter square, and 0.0013 BTD was 156 millimeter square, and therefore 6,000 is greater than 314, which is greater than 181, which is greater than 156, therefore okay. Therefore okay. We proceed to secondary bus. So you'll allow me to clean here. So secondary bus. So for secondary bus, we have said that we'll use the area of steel minimum, which is 181. So is equal to 181 millimeter square. So you will say that from table, provide H8 at 250 millimeter center to center. H8 at 250 millimeter center to center. Area of steel is equal to 201 millimeter square. And then the maximum bus spacing, maximum bus spacing So for general, the maximum bus spacing is okay. So maximum bus spacing is okay for general. You can check it for yourself. So it remains the same as for the one we designed previously. So the maximum bus spacing is the same. Again, for areas, for areas of maximum moment, again for areas of maximum moment, the spacing is okay. So no need for us to do the calculation because this is a replica of what we have already done. So the maximum bar spacing remain the same, which is okay. So this is how you present your reinforcement on the section. And remember, this is our section from this plan. And remember, this reinforcement we have not yet done with what we call reinforcement detailing. So this is just what we have designed, but I will take a very short time in our next session to discuss about reinforcement detailing of this question, and then again I will come up with the final diagram for the whole design, from the design process to the reinforcement detailing. So this one, as you can see, the bottom reinforcement, I have labeled it using numbers like 01, 02, 03, 04, 05, and so on. And the top reinforcement, I have used T1 and T2 and so on. So for the bottom reinforcement, remember for the end span, which is span A, B, B, span 1 and span 3. So here it is. These are the reinforcements. So H10 at 175. So we call it 01. And then we come to this one. This is for the mid span. For the mid span, remember this was what we designed for mid span. So this is H10 to 50. You call it 02. And then you come to end span again, H10, 175, 03. And then you come to distribution bus. This is it. So H8 to 50, 04. So you will start with the main reinforcements. So you start with 01, 02, 03. Then after finishing the main reinforcement, you come to distribution bus. So this is H8 to 50, 04. Again, here is H8 to 50, 05. The same to this will be H8 to 50, 06. And then you come to top reinforcement. We have the top reinforcement here is H10, 175, top 1. So this is top 1, the one for the one for the main. And then we come to the main at this point again, H10 at 175, top 2, this one. And then we have the distribution bus. Here it is. So this one you can label it H8 to 50, top 3. This one here. So this is H8 to 50, top 3. And this one is H8 to 50, top 4. And that is it. So I will end there for today. But remember, the question is not yet done. So we are remaining with reinforcement detailing, of which I will take a very short time to discuss in the coming session. And then we will proceed to something else. So thank you for your time. And thank you for those who have subscribed to this channel. And if you have not subscribed to the channel, please subscribe and turn on the notification bell so that you may be the first person to be notified when I upload a video. Thank you for your time. We meet again in my next session.